we learn. And I remember as a parent, when my kids were first capable of expressing themselves, I know that that's when the unending stream of questions begins. As soon as we're capable of expressing ourselves, we start asking questions. And what that really means is that we are born to explore, we're born curious, we're born to ask questions, and on the education side of the fence, we would say we're born inquiry-based learners. We also remember as parents that our infants love to poke their corner of the universe every chance they get, and they explore things like near versus far and up versus down and color and texture. And the act of poking their world is the act of demanding evidence, demanding data in return, and they have the ability to interpret that evidence, that data, and reach some conclusions. And so what they're doing is they're building up a cause and effect library. If I do this, the world is going to respond a certain way, and it gives them the ability to understand how the world around them works and how they interact with it. So the way to say this is that as parents, we know that we are born curious and we're born to demand evidence and data from the world around us and interpret that. And that second piece on the education side of the fence is we say that we are born evidence-based learners. So inquiry-based, evidence-based learning is how we learn. If you now go to the frontiers of human exploration, and let's concentrate on those disciplines that are appropriate for this program, which is STEM, science, technology, engineering, and math. Well, if you ask professionals that work in those careers, what do you get paid to do? And those professionals are scientists and engineers. They'll say, well, we are in the business of asking questions about the world. We're in the business of curiosity. That's what we get paid to do. And I would argue that it's organized curiosity, because they may be bringing powerful technologies to bear or new conceptual ways of looking at the world. And they want to ask questions in a smart way that will maximize their ability to get to an answer. So fundamentally, the act of asking the gift of a question frames a problem to be solved, and now you have to figure out some kind of experimental pathway to an answer. And so scientists and engineers are born to ask questions, rather are paid to ask questions, and they're also paid to do evidence-based learning because they poke their world in brave new ways and hopefully see something that no human being has ever seen or explained before. That's what it means to live on the frontier. The point being that we're born inquiry-based, evidence-based learners, and on the frontiers of human exploration, we pay our researchers to be inquiry-based, evidence-based learners. And in between, we insert the education pipeline, and we bring our students in at the pre-K level where they are already experts in exploration, walking into our classrooms with powerful tools in the toolbox beside them. And education is then going to dump these students out into the real world at the other end of the pipe. And we need to understand what the function of education ought to be. One set of deficiencies in terms of national education is that we don't recognize that inquiry-based, evidence-based learning is how we learn, and we therefore don't necessarily nurture the skill sets associated with that going through school. Well, what are those skill sets? The first is ownership in learning. The learner has to own the experience. And so the way to say that is that it is the student's classroom, not the teacher's classroom, and the teacher lights the way. They've got to own the experience. Other characteristics of this are problem solving and critical thinking. And here's a really important one: the ability to navigate an interdisciplinary landscape in order to secure the core knowledge necessary to solve a problem at hand. And then communications and teamwork. And that's what scientists and engineers are expected to bring to their jobs every day of their lives. And another aspect of this is, I don't know what the flavor of jobs will be in 5 or 10 years, but I know that future employers are going to look for employees that can take ownership in learning, that can problem solve, that can critically think, that can do all of those things. And so nurturing the skill sets that our kids are coming into the pipeline with is a way to inoculate them against an uncertain job market in the future. Now, what's interesting is that in the education system at a national level, we see that there are approaches that are incompatible with this philosophy. Often education systems put an enormous amount of credence on content memorization. Let's just shove as much content into those kids as we possibly can, and they end up going out into the real world and they can't critically think and they can't problem solve. It's not about the content as much as it's about embedding content in a process, in a journey. The other thing too is that we have the tendency in education to have a unidirectional flow of information from teacher to student. We don't give them ownership in learning, and education systems have a habit of beating the curiosity out of our kids. So that's not acceptable either. The next level with regard to this, and I think it's a fundamental question that we don't ask enough, is what is the fundamental goal of formal education? What are we supposed to be doing as formal educators? And I think that that's a question that we ought to ask ourselves routinely. Well, I go back to first principles. As a parent, if I am looking at my daughter Jada and my son Jordan, I know I'm not going to be with them forever. I'm going to be gone at some point, and they have to be self-sufficient, and they have to have a happy life, and they need to be able to get a good job and have a standard of living. And I want to set them up for that kind of success. And so too is formal education. Formal education is meant to prepare our kids for the real world. And if that's the case, if we're supposed to be preparing our kids for the real world, they need to understand what the real world expects of them. And if we ask, what is it that scientists and engineers do in the real world? Well, we have to bring those authentic experiences back into the classroom so that our students can see the expectation for themselves. So real world experiences in the pre-college classroom is essential if we're going to allow our students to learn what it is they're supposed to do when they leave the education system. I guess the interesting thing here are that there are two demographics with regard to STEM education. The first is the larger demographic. It's the majority of students that are not going to go into STEM careers, but they're going to be future voters, and they're going to have to make informed decisions about the use of science and technology, which means they need to understand the world of science and technology. And they're going to have to make decisions as a scientifically literate voting public on science and technology issues that affect not just their region of the country, but the entire planet. There's another demographic, which are those students that are going into STEM careers, that we've inspired to go into STEM careers. And they need to understand what is expected of them in the real world as professional scientists and engineers. And this actually goes to the heart and soul of what STEM education is all about. And if you ask teachers, you know, well, what is STEM education? They will say things like, well, science, technology, engineering, and math, it's an integrated approach to education in the classroom. But the real question, the deeper question is why? Why do we do that? Is this a flavor of education that's being embraced, or is there something deeper than that? And I guess the way to get at the answer is to ask scientists and engineers, what do you think about STEM? And from the standpoint of professional researchers, it's kind of a strange acronym, because in the real world there's no distinction. There's no distinction whatsoever between science, technology, engineering, and math. It's one seamless landscape. You have to play in that very large playground in terms of solving real world problems. And if you agree that the function of formal education is to prepare our students for the real world, then the function of STEM education should be to have real world experiences in the pre-college classroom so students get to see what is expected of them, which by definition means an integrated disciplinary landscape, that solving real problems requires an integration across science, technology, engineering, and math, because that's the way it works in the real world. And that's why there are pushes to have integrated interdisciplinary teams of teachers working together, because on the education side of the fence, we typically have these disciplines in stovepipes. There's the math stovepipe and the physics stovepipe and the reading and literacy stovepipe. And the actual nature of the world is an interdisciplinary tapestry that knows no disciplinary boundaries. So that is the motivation for STEM education. What's also interesting is that there's more to it than simply science, technology, engineering, and math. And the best way to describe this is that if NASA or the National Institutes of Health have a precious and limited research grant money, not enough to go around to all researchers that want it, which is always the case, not enough research asset to go around. The way that they equitably and fairly get that asset out to the research community is they issue what's called a request for proposals. And research teams all over the country, in absolute secrecy, design a research program around the use of that asset, and they make the case, they justify through a proposal why they ought to get that asset as opposed to all the other teams that are competing for this grant opportunity, this research asset. And every team knows that they're up against the very best minds that this nation has to offer in that discipline, because everybody's going for this proposal. And so then the proposals come into, say, NASA, and NASA convenes a proposal review board, and they use a proposal evaluation rubric to strictly grade all of the proposals. And the ones with the highest of grades get the asset, and everybody else gets nothing. And it doesn't matter how hard a research team has worked. If they get a rejection letter, the rejection letter is essentially saying, too bad, you did not prove yourself worthy enough to get this asset. That's what it's really saying, because these other teams beat you. And that announcement of opportunity, that request for proposals, may never come again. So the way to think about it is that the number of proposers that get the asset, that win the award, is small, and the number of proposers that get nothing is very large. And so the two takeaways from the professional research side are that real research is done by a very formal competition. And scientists and engineers are not just good writers, they have to be superb writers, because through the written word, they have to make a formal argument, a case for why they ought to get those assets, even though they're competing with the very best minds in that discipline. And once they do the research, they have to report out in refereed scholarly publications where they have to go through the gauntlet of a review board. So here's the problem. The problem is that if you believe that authentic, real-world experiences belong in the classroom to allow our students to understand what will be expected of them professionally as scientists and engineers, and as they move through that pipe, we educators have inspired them to go into STEM careers. And as they move into middle school and high school and undergraduate education, they start identifying what coursework they want to select in their major. So they're taking their entire educational experience and guiding themselves towards this objective, because they body and soul want to be a scientist or an engineer. And we dump them out into the real world, and if only then they say, wait a second, for me to be a practicing scientist and engineer, I have to compete? Nobody told me that. And wait a second, for me to be a practicing scientist and engineer, I have to be a superb writer? Nobody told me that either. And if that's when they found out, we failed them. We didn't do a good enough job preparing them for the real world. So real STEM is more than interdisciplinary science, technology, engineering, and math. It's transdisciplinary. It involves this boatload of communication skills, both oral and written, the ability to work in teams, the ability to communicate coherently and cogently and crisply. And so if you're going to have authentic experiences in the classroom, you have to have a transdisciplinary approach to this that includes, for instance, reading and literacy teachers. And so if we're going to create a program, that provides this kind of philosophy of approach, we need to do it in a way that is not only authentic, but is inspiring. And that's how the Student Spaceflight Experiments program came into being. Now, I see there's only 8 folks on this line, including me, Larry, and I guess Mary's on here too. I'm not sure I see. But are there any, does anybody have any questions before we move on?
Feel free to type them in the chat box if you're not using the audio feature right now, and I'm happy to orate those to Jeff.
Okay, as soon as if there's a question that comes in, just stop me and I'll go ahead and answer it. So the way that the Student Spaceflight Experiments program works is that for I think the 5th time now, we're giving Hillsborough County their own real space program. What you're getting is a flight slot to fly one of your student team designed experiments to the International Space Station and have an astronaut assigned to simply a technician to operate the experiment according to your student flight team's protocol. So Hillsborough County Public Schools is getting a precious and limited research asset because only one student team designed experiment will be selected to fly. So after all the teachers go through a formal microgravity curriculum, you then break your students into formal research teams of 3 to 5 students per team. And just like professional team in absolute secrecy will design a microgravity experiment, a microgravity research program in a science discipline of their choice, a science experiment. And that experiment needs to be designed against the real world engineering constraints imposed by the flight certified mini laboratory that everybody must use. And that experiment is constrained by the real world technology constraints of flight operations to and from low Earth orbit. And the experiment fluids and solids that comprise the experiment need to be identified, specified in terms of volumes and concentrations and pH, and there needs to be an analysis protocol. And so mathematics, the language of nature, is threading through this entire process. So this is a seamless STEM, authentic experience, mirroring how professional researchers do their thing. Now, those teams will have to write a real but grade level appropriate formal research proposal. Each team writes a proposal to make the case for why they ought to be given that one experiment slot for Hillsborough County Public Schools. And Hillsborough County takes all of those proposals together, written against a real proposal guide, just like professionals. And Hillsborough County will then convene a step 1 local area review board of local area teachers and researchers. And using the proposal evaluation rubric, you will deselect to 3 finalist proposals. You'll send those 3 finalist proposals to us. We convene the Step 2 National Review Board at the Smithsonian in Washington, D.C., and they will select your flight experiment from your 3 finalists and do the same for the other 37 Mission 13 communities. Your flight team will then have a month to optimize their experiment in a lab setting, and then we have to lock in the fluids and solids that comprise that experiment. And that list then goes to the toxicology office at NASA's Johnson Space Center in Houston for 4 months of flight safety review. Then about 2 to 3 weeks before launch, your flight team will fill and seal their flight mini laboratory and their ground control mini laboratory and ship the flight mini laboratory to Houston for payload integration. It's received by the launch services provider called NanoRacks. And NanoRacks will take all of the Mission 13 experiments together into a single payload, which has been designated SSEP Gemini. That payload will then be handed over to NASA in Houston. NASA will carry that payload to Kennedy Space Center in Florida, hand it to SpaceX. SpaceX will board it on a SpaceX Dragon spacecraft on the top of a Falcon 9 rocket. And we're projecting the launch of the Mission 13 experiments in late spring of 2019 from Kennedy Space Center. The payload of experiments, including yours, will be carried 250 miles straight up to the International Space Station, which is a vehicle the size of a football field orbiting the Earth at a speed of 4.5 miles a second. The payload will be brought aboard station. Astronauts will be assigned as simply technicians to operate the experiments for a month according to the student flight team protocols. And then the payload will be put back in Dragon. Dragon will deorbit and splash down in the Pacific off the coast of California. A recovery ship will pick it up and they will pull the payloads and air freight the payloads back to Johnson Space Center for what's called payload deintegration. NanoRacks will then photograph and inspect all of the mini laboratories to make sure there were no mini laboratory failures. And then the mini labs will be shipped FedEx overnight back to the student teams for harvesting and analysis. And you can send a delegation down to the launch to watch the bird fly. And you have the ability to send a delegation to their own very real research conference at the Smithsonian's National Air and Space Museum in Washington, D.C. So that's how this program works. It's the real space program. This is not a simulation. And it grows organically from that philosophy of approach where it is authentic, real-world STEM in a pre-college classroom that embraces the notion that our students are born as scientists, that are moving into the education pipeline as scientists, and formal education is about nurturing those skill sets and not treating education as simply content to memorize. And in those students, we see ownership and learning and critical thinking and problem solving and the ability to get content across an interdisciplinary landscape to solve whatever problem is at hand, and communications and teamwork. And I can tell you that we now have students at MIT, Stanford, Columbia, University of Chicago. Because of this program, it was the focus of their college interviews, and a lot more colleges than that. I just named a few. The young lady from North Charleston, South Carolina, that was a co-principal investigator on what was called the Tin Whisker experiment. The focus of her college interview was that SSEP experiment, and the University of Chicago gave her $40,000 a year for 4 years to attend. The young lady from San Marino High School in California is in Columbia, and Columbia gave this freshman her own research grant to continue her SSEP research. This program is inspiring, it is powerful, and it is changing the way students understand the real world of STEM. So does anybody have any questions with regard to this?
No, Jeff, this is Larry again. I just want to, again, thank you for the opportunity and that amazing overview of why STEM, you know, answering that question in our classrooms, particularly through the lens of this wide real experimentation and the transdisciplinary approach to STEM education and what this opportunity provides as a vehicle for our kids. I will also say, you know, being a part of the program for the past 5 years and making most of the visits over to the Cape to see the excitement and joy in the children's eyes as, you know, the rockets are taking off, and also the sense of pride that the students have when the projects are returned to Earth and they have the ability, usually in front of media, television cameras and the like, of determining the results or at least beginning to gather the data of that portion of the experiment. So we just recently went through that portion of last year's program, and the kids were excited, and we had news channels there to document the work. So I'll allow Mary to chime in now if she has any comments, or anyone else that may have questions. And I am keeping an eye on the chat box right now. We do have, Jeff, if just some monitoring, just folks that are saying incredible, wonderful opportunity.
Because you've got your
Okay, in fact, I just found where the chat box is.
Yeah, you can actually, if you just drag that bar over that says chat, it will create its own box too, and you can move it around. I have Dr. Lori Bradner. Is there any opportunity or collaboration with zero-G flights for teachers to fly in these experiments?
Yeah, no, unfortunately,
yeah,
no.
That would be great, right? I had the pleasure
Zero-G
my
I believe Zero-G is a for-profit company, and so, you know, I don't know how much it costs to fly Zero-G, but this is, you know, a Zero-G flight is a very, very short duration flight. You don't have much time in microgravity. And on the International Space Station, the astronauts will be operating this up to a month. The payloads will be on station for a month. And so zero-G can simply not compete with what we're offering here. So yeah, we don't have a connection to zero-G. I did it when I was partnered with NASA. We did 32 parabolic arcs. Yeah, so I think that in that particular case, NASA underwrote that mission for zero-G, but we don't have any connection to zero-G. From our first team that emailed me last week that she wants to be an aerospace engineer and wanting to know her next steps. Yeah, we hear a lot of that. In fact, the just retired director of the National Air and Space Museum, General Jack Daly, said that SSEP is probably the most important new development for the future of America's space program. We've now had over 100,000 students in this program, over, I think, 25,000 proposals, and many students have gone on into science and engineering careers and into aerospace and space science because of it. So we're very proud of this. Let me also say one other thing that I kind of thought about when Larry was talking a minute ago. You know, what you described, Larry, I mean, this is the real space program. This is not a simulation. Your students are real microgravity researchers. This is the real space program. It is newsworthy. And I think that this is something that students remember for a lifetime. But I have to be honest in that when I was creating SSEP, it wasn't about the flight experiment. I really didn't put a lot into, you know, I wasn't focusing on the flight experiment. That was only the carrot. The idea was to immerse hundreds of students at the local level in each of these communities in the thought process of how to design real experiments against real world science and engineering constraints, and how to write a proposal, a formal proposal to make a case for why your experiment should be selected, and go through a proposal review process, a real review process, just like professional researchers. So that, I think, is the power of the program, and the flight experiments are the carrot that drives it. So I think what I'll do is go on to chapter 3, and this is going to be tough. I'm going to have to kind of wing this, because normally when we're doing these video conference trainings, I'm facing a class of maybe 20 or 30 teachers, and I'm taking on the role of the instructor, and they are taking on the role of their students, and I'm modeling best teaching practices by asking leading questions and allowing them to have ownership in the learning experience. But I can't do that now because I don't hear anybody and I don't see anybody, so I'm sort of like disconnected from whoever's online right now. We can't do this through a chat box. It'll take way too long. So I'm going to try to figure out how to go through this by just giving you the content. And if anybody has a question, you're going to ask on the chat box to catch me, because I'm going to move rapidly through this. So, boy, how am I going to do this? I guess I'm going to have to provide insight into how students are going to respond to these questions. So I'm going to have to be role-playing the teacher and a commentator on the students. So first of all, you know, boys and girls, what's microgravity? And students are going to respond by saying small gravity. Well, how do you know that? Because micro means small. Well, does that make you feel like you know what microgravity is? And students will say, not really. So here's the trick. Microgravity is the technical term for weightlessness. Have you ever seen weightlessness? Have you ever watched a video of weightlessness? You probably have. You've seen astronauts in space and they're floating around. So what seems to be missing from their environment? Well, if they're floating around, it seems that gravity is missing from their environment. Why? Well, the answer typically is because they're in space away from Earth and gravity doesn't exist in space, which seems like a logical answer, and a huge percentage of students will say that. Well, that doesn't make sense to me, because I seem to recall that the reason the Earth goes around the sun is because of gravity. And the reason why the moon goes around the Earth is because of gravity, and the International Space Station is sort of like an artificial moon. So isn't gravity the cause of the of the International Space Station going around the Earth? It seems like there should be a lot of gravity in space, but there they are floating around as if gravity doesn't exist. So I really need to see this for myself, and I would love to go to the nearest spaceport in Florida, book a ticket online, and take a rocket to low Earth orbit to the International Space Station and check it out to see if the astronauts are truly floating around like gravity doesn't exist. Now, I'm going to be able to do that in the next 20 years. It's coming, but I can't do it right now. I can't book a ticket and take a rocket to space yet. So I'm going to find a really tall mountain. And you probably all know that the tallest mountain on Earth above sea level is Mount Everest. It rises about 6 miles above the surface of the Earth. That's not tall enough. What I'm going to do is I'm going to find a mountain 47 times higher than Mount Everest. It rises above the surface of the Earth 250 miles. And what's way cool about that mountain is that that's where the International Space Station orbits the Earth. So I'm going to stand on the top of my mountain. The International Space Station is going to fly right by my face. And I'm going to look in the window, the big window called the cupola on the International Space Station, really fast and see if the astronauts are truly floating around up there. And by the way, boys and girls, I took my bathroom scale with me. So I go to the top of this mountain, the International Space Station flies by, I look inside, and sure enough, the astronauts are floating around like gravity doesn't exist. And here I am at the same place in space as they are, and I stand on my bathroom scale, and boys and girls, what do you think I weigh? So this is a question to you, Larry, and to Mary. What do you think I weigh?
So I'll have to play like a student, right? So if I'm envisioning this and I'm on this huge mountain up in space, and the International Space Station is flying by, and I know from what I've seen and watching things on TV or perhaps online in the computer, things seem to float around. So my guess is I don't weigh anything because I'm floating.
Makes perfect sense, right? It's like I'm at the same place as they are, so if there's no gravity for them, there's probably no gravity for me.
Right, and that's the answer that I think most of our students would get.
Yeah, now there are other students that will say, but wait a second, you're standing on the mountain contacting Earth. You're on top of the Earth, so I think you might weigh the same as what you weigh in your bathroom on the surface of the Earth. That's a possible answer. And then
most of my students would have said.
I'm sorry?
Now we're gonna have some interesting discourse in the classroom.
Yes, you are. And you end up with a possible range of possibilities. Maybe they weigh nothing. Maybe they weigh the same as what's in their bathroom on the surface of Earth, or anything in between. Now, taking myself out of this moment a second, we sent an email to Hillsborough County asking if we could get the email addresses for the teachers that are participating in this program, so we can auto-subscribe you to the SSEP National blog. It is a critical communication pathway for teachers. It gets right to the teachers, and then the blog posts can be used right away as teachable moments in the classroom. And early next week, there's going to be a blog post that we're going to put up called "You Want Me to Take a Bathroom Scale Where?" ? And it's this story, and it takes everybody up to the top of this really tall mountain. And it asks the question, what do you think I weigh and why? And what we would like to do is have 1,000 SSEP students across the US, Canada, and Brazil write a comment and submit it as to what they think I would weigh and why, so that we can use this as a social media platform where students can get to see what their colleagues are thinking. And all of these comments are edited, so they don't go up without us looking at the comment and accepting it. So that's an important point. So then a few days.
I think, Jeff, if we stop there, and I'll allow Mary to share if she has audio capability at this time. Mary does have a small growing list of teachers that have already expressed their interest in playing along with us this year, providing this opportunity to their kids. And as you're aware, in Hillsborough, we couch this as not only a learning experience, but also a fun competition. So we do have some repeat offenders, so to speak, and some teachers that do take this to heart, and it's a highlight of their annual curriculum with their students. But we have quite a bit of new, I think, folks that are jumping on. So Mary will be able to provide that list. And what is the best way, Jeff, for us to continually update that list with you? Is it a weekly email? We hate to inundate you, every time a teacher signs up for the program.
I don't have a problem with that. If you send me a list every week, we can just add those folks easily. But it would be useful for you. Yeah, it doesn't matter. You could just append the list and send it, and we can subscribe everybody weekly. That would be no problem at all.
Great. We will do that.
I'm sorry?
We'll do that, yes.
Yeah, that's fine. So then a few days later, we're going to post the solution to that challenge after kids kind of ruminate on this a bit. And so now what I'm going to do is I'm going to go back into this, what I'm trying to do in terms of role modeling and being teacher and student at the same time. And I'm not sure this is working, but I'm trying. So I'm going to go back into this role playing now and tell you what the solution is. So boys and girls, when I stand on my bathroom scale, I will weigh 90% of what I weigh on the surface of the earth in my bathroom, almost the same. And to really understand why, we have to understand a little bit about how gravity works. And so you may not know this, but any two objects in the universe, and I've been drinking some coffee today, so any two objects in the universe, like these two coffee cups, will attract each other with a force of gravity. But I don't see these two coffee cups flying towards each other. And the reason for that is gravity is a really weak force. It's a very weak force. So at least one of the objects has to be truly massive for you to see the force of gravity in a real way. So here's my question to you. Okay, and this is Larry and Mary. Here's a question for you. Can you name two masses such that gravity between the two of them is something that you see every second of every day of your lives in a very real and powerful way? Name two masses, two objects, where the force of gravity exerted between the two is a force that you get to see and experience in a very real way every second of every day.
How about when I'm on the earth sitting in a chair?
So what are the two masses? What are the two objects?
It is the chair and myself.
So your force of gravity between you and the chair is what you're experiencing?
Yes.
So so here's a good example. If I put you here and I put the chair here, will you fly towards each other?
No.
So it can't be the chair and you that you're experiencing. It must be you and something else. And remember, I said, for you to see the force of gravity between two masses, two objects, at least one of them has to be truly massive. We know that we're not going to see a force of attraction if I put you here and the chair here. You're not going to fly towards each other. So what you want to revise your answer maybe?
Got any ideas for it? All right.
You don't want to revise your answer maybe?
Yes, we have our wonderful Earth.
Okay. The two masses that we're talking about are you and planet Earth. You and planet Earth. The Earth is truly massive. And the force of gravity exerted by the entire planet on you is pulling you down. And what's interesting is that we may have never thought about this before because you were born into a world of gravity. But for some reason, if you were to jump as hard as you can, if you really jump, you don't keep going. It's like some magic force comes and grabs you back to the surface of the earth, and it comes out of the blue. It comes out of nowhere. And we're not even quite sure where it comes from. But there is a real force of attraction, a force of gravity between any two objects. And when one is massive, you get to see the force in a big way. So the force of gravity between the earth and you, that the force of gravity exerted by the earth and you is pulling you down, and that's what's keeping you in that chair. And that's what allows you to walk, because every step you take, the earth pulls you down so you can take another step. Now, does anybody know what we call the force of gravity exerted by Earth on you? It has a real special name, and you all know the name, but you might not remember where it's filed, because you have to make that connection. What's the force of gravity exerted by the planet on you? It's called your weight. Your weight. So when you go on a bathroom scale and it says maybe 150 pounds, what that is saying is that the entire mass of the planet is pulling down on you with a force of 150 pounds. That's what your weight is. Now, let me ask another question. What do you think happens to the force of gravity when we take two objects and we move them farther apart? What happens to the force of gravity between them when we move them farther apart? Anybody want to guess? It gets weaker. Thank you, Danielle. Okay, it gets weaker. And that seems kind of intuitive, because it's sort of like if I move this cup to infinity, and beyond, how does this cup even know that one exists? The force of gravity gets weaker the farther the objects are away from each other. So here's my question. The force of gravity exerted by planet Earth on you, your weight, critically depends on the distance you are from the Earth. So how far are you from the Earth? You're standing on the Earth. What is the distance between you and planet Earth? Anybody want to guess that one?
My hand is up, Jeff. My hand is up. I say there's no distance. I'm standing on it.
So tell me the answer. What's the distance between you and Earth?
Well, as a student in class, I'm saying I'm sitting here. I'm standing here in school. I can't be. I have no distance from Earth. I'm on Earth.
Okay, that's a really good answer. You have no distance from Earth. But now let's look at this. Here you are in Florida right now. Is it true that half the Earth is farther from you and half of the Earth is closer to you? Would you agree with that? If you're standing in Florida right here, is it true, and in fact, standing anywhere on Earth, is it true that half the Earth is farther from you and half the Earth is closer to you? Yes or no?
As a student who may not have traveled out of my neighborhood, that would be I think conceptually a hard question. So I think they would probably say, because they're going to say yes. If it's an answer, I'm going to say yes. Half the Earth is far away from me, and the other half of the Earth isn't far away from me.
Okay, so let's use this physical model.
Chris, from my classmate, what else might students say?
Well, let's use this physical model as a way to explore that. So the first question that I have to ask is, does anybody know the diameter of the Earth? How deep a hole would you have to dig to get to the other side? Now, a lot of students know that the United States right here is so wide that if you wanted to travel from California to New York across the United States, it's about 2,500 miles, 2,500 miles. And you can use the United States as a little ruler, and you see a little over 3 United States will go across the Earth. The Earth is 8,000 miles across, which means that if you wanted to dig a hole from where you are to the other side, that hole would be 8,000 miles across, and there is stuff on Earth pulling on you that's right under your feet, and there is stuff pulling on you from Earth that's 8,000 miles away, and there is stuff making up the Earth anywhere in between that is pulling on you as well, so that all of the mass of the Earth, when you add up all of the force exerted on you, that is your weight. It's the mass of the entire planet pulling on you, from the stuff under your feet to the stuff 8,000 miles away. So now, if I look at this model and I'm standing over here and look at this ring, okay, this half of the planet is closer to me, and this half of the planet is farther from me, but all of the planet is pulling on me. So if this half of the planet is closer to me, and this half of the planet is farther from me, on average, how far is planet Earth from me? On average, how far is planet Earth from me?
Danielle has a couple of comments. Putting on her student hat, I'm sure. She said, does that mean we're talking about the core? And then also, as a student, does that mean that my classmates are pulling on me too?
Well, the answer is yes, the core. So in other words, on average, you are the radius away from Earth. So if the diameter is 4,000 miles, the radius, I'm sorry, is 8,000 miles, the radius is 4,000 miles. Another way to say it is half the Earth is farther from you than 4,000 miles, and half of the Earth is closer to you than 4,000 miles. So on average, the Earth is 4,000 miles away. And the way that we say that correctly is that the distance between two masses, two objects, is the distance between what are called the centers of mass. So the center of mass of the Earth is the center of the Earth, and the center of mass of me is in me. And the student oh look, it's like this is going to be very helpful to explain to my students. I'm learning stuff I didn't even know. Exciting, very good. And somebody asked a question that kind of scrolled by, does that mean that your student classmates are pulling on you too? Yes, it does, because any two objects in the universe attract each other with a force of gravity, but unless one is really massive, you won't see it, because gravity is an incredibly weak force. So now, let me go ahead and do this. If this diameter is 8,000 miles, and I go to the top of a mountain 250 miles high, which is where the International Space Station orbits the Earth, is the top of my mountain out here? Is it out here? Where would you put it? Is this too far or too close? Again, the ball is 8,000 miles across. The mountaintop is 250 miles above the surface of the Earth. So where would I put my mountain? Out here?
I would say maybe just a finger width away.
Not even. Yeah, Danielle said it, as a student, right against the Earth almost. Yeah, it's really close to the Earth's surface. 250 miles is not very high above the Earth. But are the astronauts and me, because I'm at the same location as the astronauts, are we in outer space? The answer is yes. We are in outer space.
Putting on my student hat, yeah, I'm going to say every time I see the International Space Station on TV or in artwork, it seems like it's dark. Why is that?
Yes. It's
That's the same as outer space?
Which means that the International Space Station is above Earth's atmosphere. International Space Station is above Earth's atmosphere, which means that we, as bottom dwellers under this vast ocean of air, we are living under a thin veil of air. And a good way to say it is the atmosphere compared to Earth is thinner than the skin of an apple compared to an apple. You can actually do that experiment. You can measure the skin of an apple compared to an apple, and the atmosphere only goes up 100 kilometers, 60 miles. Think of a town, a city, that's more than 60 miles away from you right now, just 60 miles. That city is farther than outer space. Outer space is close. And all of life requires this atmosphere, all of life on Earth. And we are changing this atmosphere. We humans are changing this atmosphere. And that speaks to the fragility of the environment around us. And it also speaks to the need for a scientifically literate voting public that can make informed decisions about the use of science and technology and understand that we cannot keep pumping fossil fuels into the air, and we have to go to clean energy because the future of the human race depends on it. It's that dire. So if you want to ask where is the International Space Station, it's really close to the surface of the Earth. And if you want to see what the International Space Station astronauts see when they look out their window, this is what they see. Check it out. This is so cool. That's what they see. Now, here's my question. If I'm standing on my bathroom scale in my bathroom on the surface of the Earth, how far am I away from Earth? We just went through this. So how far am I away from Earth? 4,000 miles. If I'm now standing on my mountain 250 miles above the surface of the Earth, how far am I away from Earth? 4,250 miles. Have I moved very far away from Earth? If I go from 4,000 miles away from Earth to 4,250 miles away from Earth, have I moved very far from the Earth? Well, actually, relative to the size of Earth, we're really close to the surface of the Earth, which means that the force of gravity, my weight, cannot have gone down much. Remember, the bigger the distance between two masses, the less is the force of gravity exerted. So the force of gravity exerted by Earth on me, my weight, can only go down a little bit by going to a mountain so close to the surface of the Earth. Everybody understand that? I'm counting on Danielle. Yes. Oh, Mary says yes. Okay. That's why I weigh 90% of what I weigh in my bathroom when I'm on top of the mountain. Okay? That's why I weigh 90%. My weight has only gone down a little bit because I haven't gone very far from the Earth. But here's my question. Am I at the same location in space as the astronauts? In other words, am I at the same distance from the Earth as the astronauts when I'm on top of my mountain? Remember, they went right by my face. I looked in the window. They were floating around. The answer is yes, I'm at the same location in space as the astronauts. So what is the weight of an astronaut? The weight of an astronaut must also be 90% of what they weigh on the surface of the Earth. They are not weightless. The force of gravity exerted on those astronauts is almost identical to what they weigh in their bathroom on the surface of the Earth. It's 90% of the weight as compared to the bathroom. And the weight of the International Space Station is 90% of what it would weigh on the surface of the Earth if you could find a bathroom scale the size of a football field to put it on. The astronauts are not weightless. Gravity is alive and well in outer space. We knew that because we know that the moon goes around the Earth because of gravity, and the Earth goes around the sun because of gravity, and the International Space Station goes around the Earth because of gravity. So now, what's the problem, boys and girls? I'm waiting for somebody to type it out. I'm actually curious now. How do they float in capital letters? Thank you, Danielle. And so I've never done this through chats. This is normally an interaction with live bodies that I can see, okay? But this is working. Well, this is good. This is
working. It's working. Thank you for your flexibility.
It's working. So now, what I have to do is I have to admit something to you. I happen to be, I know, from a Floridian's vantage point, this is not necessarily a good thing, but I'm a New Yorker. Though I hear there are a lot of retired New Yorkers in Florida, and I happen to be from the Bronx. And my favorite building is the Empire State Building. And so if I go to the top of the Empire State Building, Danielle, hi! Hi! If I go to the top of the Empire State Building, I am now 104 floors above the surface of the Earth. How does the top of the Empire State Building compare to, say, the top of Mount Everest? I see Danielle typing. And she's saying, yeah, I'm not sure. Okay, she says, like a toothpick in comparison. Yeah, I would say that, yeah. The Empire State Building is really close to the surface of the Earth, even the top floor, and the Mount Everest is much higher. So if I compare the Empire State Building to a mountain 47 times higher than Mount Everest, we know that the Empire State Building is really close to the surface of the Earth. So if I go to the 104th floor of the Empire State Building and I step on my bathroom scale, what will I weigh? The same
Almost
in your bathroom. in my bathroom on Earth. Virtually the same thing. You'd need a very sensitive instrument to detect it. So now what I'm going to do is I'm going to go up in the elevator from the ground floor to the 104th floor. And inside the elevator is me, my bathroom scale, and a little chair, so that when I stand on the chair, I am 1 foot above the floor of the elevator. So I take the elevator to the 104th floor, the doors open up, the elevator is not moving. It's like the elevator is part of the 104th floor. And I get up on my chair and I step down on my bathroom scale, and boys and girls, what do I weigh? It's not a trick question. I weigh the same as what I weigh on the surface of the Earth in my bathroom. Now I get back up on my chair, and the doors of the elevator close. And the moment I am walking off the edge of the chair, somebody cuts the cable on the elevator. Now, what happens to the elevator? What does the elevator do?
Fall.
You drop. You start falling. And what's happening is the speed of the elevator is increasing. And whenever something has a speed that's increasing, we say that it is accelerating. The elevator is accelerating down. What's causing the acceleration? What's causing the elevator to accelerate down? The force of gravity exerted by planet Earth on the elevator, which means the force of gravity exerted by Earth on the elevator is the elevator's weight. It's the elevator's weight that is pulling it down. That's what's causing the acceleration. Now, are there any other forces besides the force of gravity exerted by Earth that are acting on this elevator? Are there any other forces? Friction. So the elevator might be rubbing up against the side walls of the shaft, but let's say we had really good engineering and there's no friction with the side walls of the shaft. Is there any other force? Air resistance. Very good. The shaft is full of air. Thank you, Danielle. This is great. This is teamwork. Okay? So there is air in the shaft. And you may not know this, boys and girls, but as you move through air, there is a resistance to motion. There's a drag force. And the faster the object is, the bigger the drag force. So one way to think about it is if you're driving in a car at 10 miles an hour and you put your hand out the window, you'll feel the air push you back a little bit. But on the highway, if you put your hand out the window at 50 miles an hour, the air really pushes you back. And so the higher the speed of the object, the bigger the drag, the drag force. And a good way to think about it is if you go parachuting and you jump out of a plane, well, you start accelerating for the first couple of seconds, but then as you pick up speed, the drag, the air resistance increases until it finally stops you from going any faster, and you reach what's called the terminal speed. For a human being, it's about 100 miles an hour. And so you don't go any faster than 100 miles an hour because of the air resistance, but you can't survive getting down to the ground, impacting the ground at 100 miles an hour, so you better deploy a parachute to slow you down quite a bit. That's how it works. But now what we're going to do is we're going to suck all of the air out of the elevator shaft. Now, are there any other forces acting on the elevator besides the force of gravity exerted by Earth? And it's a simple answer. The answer is no. The only force acting on that elevator is the force of gravity. And what do we call it when something is falling? It's a special kind of falling when the only force acting on it is gravity, the force of gravity. It's a very special kind of falling. Yes, it's free fall. Now, if it's freely falling, if the force of gravity is the only thing acting on it, will it keep accelerating? Well, it will eventually hit the surface of the Earth, but if it's a really deep shaft and it keeps going through deeper into the Earth, it'll keep accelerating. It'll keep going faster and faster and faster. Now the question I have is, the elevator car is accelerating. I am accelerating down. The bathroom scale is accelerating down, and so is the chair. Are we all accelerating down at the same rate? Are we going together? Now, you might think, I don't know. Maybe we are, maybe we're not, maybe, as Danielle says, sort of, okay? Well, I'm Dwayne Johnson, I'm The Rock, and this is when he had hair, I guess, I don't know. And so I'm holding a Volkswagen Beetle in one hand, and I'm holding a bowling ball in the other hand. And now what I'm doing is I'm taking all the air out of this room. So I have a really heavy Volkswagen Beetle, and comparatively speaking, a light bowling ball. And I drop them in an airless room, so there's no air resistance, from the same height at the same time. Will they both hit the ground at the same time? Heavy object, light object. Will they both hit the ground at the same time? You might not know. It might not be immediately obvious. But wait a second. Depending on the weight of this bowling ball, can I think of the car as maybe 416 bowling balls? Can I think of the mass of the car in bowling ball units? So depending on the weight of this bowling ball, this car could be the equivalent of 416 bowling balls. And so now if I drop 417 bowling balls, 416 represent the car, and I have my other one here, and all of the bowling balls are absolutely identical to each other. If I drop all 417 bowling balls at the same time from the same height, will they hit the ground at the same time? Anybody? I hear typing. My screen froze. Force of gravity is the same. Well, the force of gravity on each bowling ball is the same, which means that each bowling ball is going to hit the ground at exactly the same time. But if these 416 bowling balls represent the mass of the car, then the car is going to hit the ground at the same time as this bowling ball, which means that the acceleration due to gravity has nothing to do with the mass of the object you're dropping, because you can always think of a heavy mass as a lot of little masses. And if you compare this mass here to a lot of little masses here where they're all identical, they're all going to hit the ground at the same time, which means that I and the elevator, car itself, and the chair and the bathroom scale are all accelerating down together. Now, does that mean that I am accelerating towards the surface of the Earth? Is my body accelerating towards the surface of the Earth? Yes. Are the floor and the bathroom scale accelerating towards the surface of the Earth? Yes. Now, are they accelerating together? Yes. Does that mean that if I move down a certain distance, the floor and the bathroom scale will move down the same distance? If I move down a certain distance, the floor and the bathroom scale, will they move down the same distance since we're accelerating together? The answer is, I don't see anybody answering. The answer is yes, because if we're all going down together, if I move down a certain distance, the elevator floor and the bathroom scale move down the same distance. And this all started when I was standing on the chair, a foot above the floor, the cable was cut, and everything started accelerating at the same rate. And now, in my elevator, I cannot see the rest of the world accelerating by me because there are no windows in the elevator. But I do know that I cannot get to the floor, because every time I travel a certain distance in the direction of the floor is moving away from me at the same distance, in the same distance. I can't get to the floor. And so in my elevator, I am floating 1 foot above the floor in an environment where it seems as if gravity's been turned completely off. Now, what's kind of cool about this is there's an irony. It is the force of gravity exerted by all of planet Earth that is causing the elevator to plummet. I'm sorry, but how did your feet leave the floor of the elevator if everything falls at the same time? Because remember, I started on the top of a chair. I stood on top of the chair again, which was 1 foot above the floor. And the instant I was walking off the edge of the chair, somebody cut the cable, and everything started accelerating together, which means I thought I was going to head to the floor, but the floor is flying away from me at exactly the same rate I'm flying towards it. I can't get there. So the irony is that the force of gravity exerted by planet Earth on the elevator and everything inside it, our weight, is causing us to accelerate down at a very large acceleration. But the irony is that inside a freely falling laboratory, everything will behave as if gravity doesn't exist, which is way cool. Now, let me just see, the last Skype I did, I used my ping pong balls. Give me a minute, I have to pick them up. Okay, so boys and girls, if there's no air in this room, this is the elevator. Watch. It's the elevator, it's in free fall. Here's a question for you. Let's say I took this ball, no air in the room, no air resistance. If I throw it, so I give it a certain force, which takes it up to a certain speed. So I give it a certain initial speed by providing a force with my fingers. Once it leaves my hand is not providing a force on this ball anymore. And this ball will follow a path that looks like this. Everybody knows that. Everybody who goes out on a ball field and throws a ball or kicks a soccer ball or throws a football knows that it follows this kind of arced path, right? So when I throw this and there's no air in the room, once it leaves my fingers, it has a speed and it's going to arc like this. Is it in free fall? Is that in free fall? Anybody there? I don't know. No, because it had a force to start. Well, free fall means that at any moment, the only force acting on the object is gravity. So I gave it an initial speed, but once it leaves my hand, the only force acting on it is gravity, so it's in free fall. Does everybody see what I just said? Okay?
Mm-hmm.
Now, if I throw it a little faster and it leaves my hand, it then goes into free fall, but the arc it makes takes it farther away from me. And if I throw it even faster, the arc gets even bigger. And if I keep throwing it faster and faster and faster, and I launch it like in a cannon, the arc goes maybe to the next town. And if I keep throwing it faster and faster and faster still, what's going to happen is as I throw it out this way, if it's a really high speed, as the force of gravity of the Earth causes it to arc, the surface of the Earth curves with it, and it goes completely around the Earth, and it comes back, and I can catch it in 90 minutes. And it never intersected the Earth. It never saw the surface of the Earth, because I threw it so fast that as gravity was arcing it, it was following its trajectory. The surface of the Earth is now curving with it, and it comes back and lands in my hand. Does everybody understand that? So that's how the ISS travels around the Earth. Yeah, okay. Another way to say it, this is the elevator in free fall. This is the International Space Station in free fall. It's the same thing. This is the Earth going around the sun. This is the moon going around the Earth. This is the entire solar system going around the center of the Milky Way galaxy every 250 million years. And one galactic year ago, the dinosaurs roamed the Earth. It's all the same. I'll tell you something else, boys and girls. Every time you throw a ball on a ball field and it hits the Earth and stops, if you can imagine what would happen if the Earth did not stop it, but the gravity from Earth kept it going, it would go into the Earth, it would accelerate, it would go past the center of the Earth. Now most of the Earth is above it, and the Earth says, come back. And it comes back, and it pops out of the Earth over here, and it lands in my hand. Boys and girls, every time you throw a ball on a ball field, you're seeing a piece of an orbit. It's all the same thing. It all comes from a simple mathematical equation that Isaac Newton gave us a few hundred years ago. So my point is that the International Space Station is in free fall. It's a freely falling laboratory. The only force acting on it is gravity. Everything is accelerating together. And falling does not necessarily mean getting closer to the Earth. Falling, freely falling, only means that gravity is acting on it. And in this particular case, you can put the International Space Station in a really good circular orbit, never getting closer to the Earth, never getting farther from the Earth. So what I said, to kind of wrap this in a like nice bow here before we move on, is I first asked you, what is microgravity? You said small gravity. I said, but wait a second, does that really help you understand what microgravity is by translating the word micro? You said no. So I said, well, maybe I can help. Microgravity is the technical term for weightlessness. Has anybody ever seen videos of weightlessness? Yeah, I've seen astronauts floating around in space. What does it look like that environment is missing? Gravity. Why? Because there's no gravity in space. Well, that doesn't make sense, because why does the Earth go around the sun? I think that's gravity. I'm not sure. I need to see it for myself. So I go to the top of a 250-mile-high mountain, which is at the height of the International Space Station's orbit, and I'm going to look in the window, the cupola, to see if they're floating around like gravity doesn't exist. And I do, and they are floating around like gravity doesn't exist, and I'm at the same location in space as they are, and I stand on my bathroom scale, and lo and behold, it's not that I weigh nothing. I weigh 90% of what I weigh on the surface of the Earth in my bathroom, almost the same. And the reason for that is on the surface of the Earth, I'm 4,000 miles away from the Earth. But when I go to my mountain 250 miles high, I'm 4,250 miles away from the Earth. I haven't gone very far from the Earth at all, which means that the force of gravity exerted on me, my weight, only goes down a little bit. I'm still 90% of what I weigh on the surface of the Earth. But if the astronauts on the International Space Station are at the same distance from Earth as me on my mountain, the force of gravity exerted on them, their weight must also be 90% of what I weigh on the surface of the Earth. That's what's happening. But then why are they weightless? So I took you to the top of the Empire State Building. We put you in an elevator. I took the air out, so the only force exerted on the elevator was gravity. I cut the cable. We saw that everything accelerates together, which means as I'm going down a certain distance, the floor of the elevator and the bathroom scale are going down the same distance, which means I can't catch the floor. I am weightless in the middle of the elevator. Am I truly weightless? No. The force of gravity exerted by Earth on me, my weight, is what's causing me to accelerate. But in that accelerated frame of reference, in that freely falling laboratory, everything thinks that they're weightless. Everything will behave as if gravity's turned completely off. I could push off one wall and float to the other side. I can push off this wall and float to the other side. And then I showed you that a ball thrown really fast is freely falling around the Earth just like the elevator. The astronauts are weightless because they're in a freely falling laboratory. Are they truly weightless? No, it's the force of gravity exerted by Earth that is causing them to fall. But they seem to think, and they behave, and everything you put in that laboratory will behave as if gravity's turned completely off. And to get the International Space Station to orbit the Earth like that, I needed to give it a very large horizontal speed. There was no big hand that threw it. We used rockets. That's what rockets are for. So does everybody understand how this works? Do you think, since this is written up on the website, do you think that you can facilitate this kind of conversation and using these leading questions, get them to be able to tell this story with you so that they have ownership in this experience?
Jeff, this is Larry. I think we have some extraordinary teachers in our district, but I think it would be a stretch of all of our abilities to be able to do it as well as you've just done it. But I think we're in a good space. The folks that are on the call right now probably agree with me there. I have a question though. I think I know the answer, but students might ask, going back to your original ping pong example before we started throwing it and putting an arc, dropping it and using the elevator example, we have theme parks right down the street in Orlando, and many of the students probably have some sort of familiarity with perhaps Hollywood's Tower of Terror, which is a simulation, or I guess a replica of an elevator that free falls. So the question the students might have is, I'm going to fall safely with the elevator. Why does Disney require me to wear a lap belt or a seat belt?
I'm not familiar with the ride, so I don't know exactly how it works. It sounds like it's a ride where for the first couple of seconds you actually feel a pit in your stomach when you're actually in free fall, because your organs that are normally pulled down towards your feet by the force of gravity, that force of gravity goes away. So for those first few seconds, all of a sudden there's a repositioning of all your internal organs, and you feel that pit in your stomach. That's what that experience is. But after a first couple of seconds, if this is happening in air, the air drag keeps you from going any faster. If you get up to 100 miles an hour, that is. But I would need to understand the ride exactly in terms of exactly what it's doing, and maybe there's a rotation involved, which involves what's called the centrifugal force, which is a force that's experienced by the rider that is moving around in a circular trajectory. With regard to the other comment that you made, the video is being taped, so you have this to share, so you can share at least how I would do it in a classroom, and this is all written up on the website as well, so there's lots of resources. Now let's move on to the next part of this, and so you're still boys and girls. So now, boys and girls, if I want to explore some system, whether it's a physical, chemical, or biological system, the question is, what does that mean? What do I do? Well, let's say the system is a germinating seed. So I want to explore a germination in the seed. Is the seed the only thing I need, or do I need something else? What else do I need just besides the seed itself, or seeds?
Well, we all know that.
I'm sorry?
Sorry, with my student hat on, we think all seeds need water to grow.
So you might need water, you might need temperature, you might need a soil with a certain composition, you might need an atmosphere with a certain composition, you might need light. So whenever we're studying a system, it's really whatever is under study and its environment. Is it true that no matter what system I want to study, I can list characteristics of the environment? Is that true? Does everybody agree with that? No matter what system I want to study, I can always list the characteristics of its environment. And a related question is, what do we call that list of characteristics? I'm looking for a V word like Victor. What do we call those characteristics? Variables. And the way that scientists poke their corner of the universe, like our little infant kids, right? The way that scientists poke their corner of the universe, what they do is you have to change the variables and see how the system responds. That gives you insight into how the system works. But you want to do it in an organized curiosity way. You don't want to change all the variables at once, because then you don't know which variable is responsible for what you're seeing. So the way that it's done, in real research, in classical research, is to keep the variables constant, find a variable that you're interested in, and change it and see how the system responds. And we call that the what, because Danielle just did this in her class today. Yes, it's the independent variable. So let's say that the Acme Seed Company says, we have genetically engineered a species of wheat that grows really well in very, very dry climates. So I now want to see whether or not they're telling the truth. I want to see if this species of wheat actually does grow really, really well in dry climates. So what is the independent variable that I'm interested in changing and seeing the response of the wheat? What's the independent variable? Say one more time. So The Acme Seed Company has a genetically engineered species of wheat that they claim grows really, really well in very dry climates. I want to test to see whether or not they're telling the truth. I want to see if this species of wheat really does grow well in dry climates. So I need to grow it. And what is my independent variable, the variable I'm interested in? Well, it is the climate, but I'm giving you a hint. It has to grow really well in dry climates, which means, yes, Mary, you're right, the amount of water. So what I want to do is I want to understand whether or not I get a lot of food production for a little amount of water. But for me to determine that, is it enough for me just to grow this new variety of wheat, this new species of wheat, where I don't know anything about the species of wheat? I'm actually putting it to the test. Is it enough to just grow that species of wheat? What else do I have to grow? I have to grow regular wheat. Wheat that I'm familiar with, yes. Wheat that I know about, wheat that we understand. And that's what we call the control experiment. And so what I want to do is I want to grow regular wheat and this genetically engineered wheat, and I want to show that I get the same food production, but the genetically engineered wheat took less water. Does everybody agree with that? That's classic science. Okay. Now, there is one variable that plays a critical role in the vast majority of systems we would want to study. A variable that needs to be the independent variable. And for us to understand the role of that variable in the system, we need to change it. But this variable is typically taken for granted. Does anybody know what that variable might be? Gravity. Gravity. And just to give you an example of why gravity is so important, even a germinating seed knows about gravity, because when it germinates, the roots go down and the shoots go up. That's called geotropism. Your body, every time you take a step, the weight of your body compresses your bones, and it sends a bioelectrical feedback back to your body saying, we got to keep bone production up. We need bones. Bones are good. But in a microgravity environment where the astronauts are, there is no bone compression, because in their environment, they perceive everything as weightless. And so their bodies say, oh, we don't need bones anymore. And the astronauts start excreting their skeletal system. That's what happens. If you take a look at a body of water, fresh water, maybe a lake, the life winters over in that lake. The top, what happens is that the water turns to ice, and the ice floats. The reason it floats is because of a buoyant force. The buoyant force is due to gravity. There is no buoyancy in microgravity. And so because the ice floats, it acts as a thermal blanket so that the water down beneath it does not freeze, and life can survive in that body of water over winter. Gravity is everywhere. And if you want to understand the role of gravity in some system, which is physical, chemical, or biological, you need to change the force of gravity as the independent variable and see how the system responds. But here's the point. Is there any laboratory on the surface of the Earth where I can fundamentally change the force of gravity exerted by the planet on the system under study, like changing temperature or changing humidity? Is there any way that I can change the force of gravity exerted by planet Earth on the system? I can't. There's no such thing as an anti-gravity room where some mechanical equipment makes gravity disappear. You can't do it. And even if I went to a mountain 47 times higher than Mount Everest, and I put a laboratory up there, how much does the gravity variable change? Anybody? Just 10%. It only goes down 10%. It's still 90% of what it is on the surface. So the only way to do this is try to find a creative way to trick the system into thinking that gravity went away. How do we do that? You put it in free fall. because anything you put in free fall will absolutely behave as if gravity does not exist. And so one way to do it is put it in an elevator, take the air out of the elevator and cut the cable and let it accelerate. They exist. They're called drop towers. NASA has them, universities have them, and they put their system under study in a little elevator car, and they pack it with sensors and video cameras, and they drop it, and they watch it as it goes down. But how long do you think they have in weightlessness in a drop tower? How much time do you think they have? Only a few
Just
seconds.
a few seconds?
Yes, only a few seconds. And is it possible that what you're studying might take minutes or hours or days or weeks or months to do its thing? Is that possible? So where would you go, boys and girls, to find a continuously freely falling laboratory to run your experiment? And that's one of the main reasons it was built, the International Space Station. So we run our experiment in orbit in a weightless environment, and your system will behave as if gravity is turned completely off. But is it enough to run your experiment in orbit? You have to run an identical experiment on the ground in gravity. So the flight experiment, when it comes down, this experiment ran in the seeming absence of gravity. This experiment ran in gravity, and that is your control here on Earth. And when you compare the two experiments, the variable that you changed is the gravity variable, and you look for differences in the system, which can be telltale signs of the role of gravity in that system. Does everybody understand that? So the idea here is to, in classic science, to understand how a system behaves, you want to keep the variables constant and change one, the independent variable that you're interested in, and see the response of the system. But in the case of gravity, it's a really strange variable to do that with, because we don't have the ability to change the force of gravity exerted by Earth. But we do have the ability to put the system in free fall, continuous free fall, where it will behave as if gravity is turned completely off. And when we compare that to the ground control experiment operated in gravity, we can discern the differences due to possibly the gravity variable, the role of gravity. So the entire program, SSEP, grows from one essential question. What physical, chemical, or biological system would I like to explore with gravity seemingly turned off for a period of time, in order to assess the role of gravity in that system? So is everybody capable of facilitating that understanding with your class? So now, the mini laboratory, and I don't happen to have one here, disappeared. The mini laboratory that we use is a tube about 7 inches long, and it can be divided up to 3 chambers, 3 volumes, by adding 2 clamps. So the mini laboratory that you use is essentially 3 test tubes that of fluids and solids that you can take to the International Space Station, which can be combined in a prescribed way by opening a clamp and shaking it. Now, the technology of flight operations dictates that you have to submit your flight experiment to Johnson Space Center a few weeks before launch, and the launch could be delayed. Do you want your flight experiment, your microgravity experiment, operating on the ground in gravity for a few weeks? No. So it may very well be, because of that technology constraint, you need to put the experiment up in an inactive state, and then the astronaut activates it. And then it'll take a few days from the time it splashes down to get back to your student team. Do you want your flight experiment operating in gravity while it's being transported across the surface of the Earth to your student team? Probably not. So you might need to shut the experiment down before it deorbits. And this is why that 85% of the experiments are biological in nature. And so the reason for that is that lower grade levels, there is an infinite variety of dried seeds that can be hydrated on orbit. Even fairy shrimp come in a freeze-dried form. There are a bunch of biologicals like that. And there's also at upper grade levels hundreds and hundreds of microbiologicals that are available in a freeze-dried form that can be hydrated on orbit. So you can do some very sophisticated experiments here. And we know that biology operates differently in microgravity. That's not to say that there are indeed physical and chemical systems that are done as SSEP experiments like oxidation. But most of the experiments are biological in nature. And biology can be killed and preserved by introducing a fixative like alcohol or formaldehyde or glutaraldehyde. So I think it was one of your experiments, I could be wrong here, where students at the 6th grade level wanted to determine whether or not seed germination rates were the same in microgravity. And the justification in their proposal was, hey, the astronauts are going to have to grow their own food for long duration space flight or colonies somewhere else. So we better know if the germination rates are the same. So in the first chamber, they put dried lettuce seeds. And in the second chamber, they put distilled water. And in the third chamber, they put alcohol, which is a fixative. In orbit, the astronauts opened the first clamp and they shook it, which hydrated the seeds, and they should have germinated 12 days later. So then the astronaut opened the second clamp and introduced the alcohol to kill and preserve the seedlings. And the same thing was happening on the ground at the same time. So when the flight experiment came down, the students could count how many seeds germinated in space, and they could count how many seeds germinated back on Earth, and they could look statistically as to whether or not it was a statistically significant difference to see whether or not the seeds germinated differently in space. So would it be more difficult to do an Earth science experiment? Typically, yes. So for instance, but we do have Earth science experiments, and when I take you to the website, I'll show you where to look at all the experiments that have been selected for flight. We do have Earth science experiments too, but this is mostly a biology program. So what was I saying? I was saying yes. So one of the high school teams wanted to understand whether or not salmonella was more virulent in a microgravity environment. So they put freeze-dried salmonella in the first chamber. They put a Luria broth growth medium in the second chamber and glutaraldehyde, a fixative, in the third chamber. Once it got to orbit, the astronaut opened the first clamp and shook it to hydrate and activate the salmonella. It grew for 2 days. Then they introduced the fixative glutaraldehyde to kill and preserve it. The same thing was happening on the ground. And when they brought the experiment down, this team was actually working with a researcher advisor at MIT that allowed the students to use some pretty sophisticated laboratory equipment. And they were able to measure the colony size to see if the colony grew faster in space, which would mean that it's more virulent in space, which would pose a health risk to the astronauts. And they were also able to measure any structural differences, observe structural differences in the salmonella using high definition microscopy. So does everybody understand how these two are examples of experiments? So what you need to understand is that they're designing real experiments against real world engineering and technology constraints. In this particular case, the technology constraint is you can't put the experiment right up. It's going to be on the ground for a few weeks. You can't bring it right down. It's going to take a few days. And so you may want to have your experiment activatable on orbit and deactivated before deorbit. And that's why 85% of the experiments are biological in nature. Now, when you go to the website that has all of the flight experiments that were selected, you can go through 240 experiment write-ups, and you can see what the Earth science experiments were. There are Earth science experiments. There are oxidation experiments, which can be part of an Earth science unit. And I'll take you there in a couple of minutes. So is everybody with me on this?
Yep.
So what I did so far was I provided the underlying pedagogy for why it is important, if education is meant to prepare our students for the real world, in STEM education, why it's important to have authentic research experiences in STEM in the classroom so that our students can understand science and technology, how they really work in the real world, and can understand what is expected of professional scientists and engineers. And we said that that has to be an interdisciplinary team, in fact, a transdisciplinary team, because reading and writing skills and communication skills are vital because real researchers write real proposals. Then I walked into how this program grows organically from that philosophy of approach, how this program delivers on that philosophy. And then I walked through the story arc of the curriculum, which is what is microgravity, what causes microgravity, why would you want to do science in a microgravity environment, because you're trying to understand the role of gravity in some system under study, and how do you think about getting students to frame designing microgravity experiments. And I gave you examples of 2 in these tubes. So is everybody with me so far? All good? Okay. So now what I'm going to do is I'm going to take you to the last chapter, which is the website. Can you all see the website here? Looks like you can.
Yep.
Okay, let me see if I can zoom in a little bit. Okay, let me do it again. Okay, so you ready? All right, so now this is the SSEP website, and you can tell because there's an International Space Station against a black sky. Do you see my cursor? Are you able to see my cursor?
Yes, and Jeff, that should show up without issue on the recording.
Okay, good. So what I'm going to do is walk across the navigation rows here. There are actually, it's not, I can't zoom it. Let me zoom out to normal size. Okay. So I'm going to walk across the navigation row, the lower one. So if you want to read 1,016 currently media articles written about this program since this program started, you can go to SSEP in the news, and all of the links to all 1,000 plus articles are there. If you want to read about our strategic partners that make this program possible, you can go there. If you want to read about our national partners that make this program possible, you can go there. If you want to read a few hundred bios of every one of the review board members at the Smithsonian that select the flight experiments, you can go to the review boards page. If you want to download logos and banners, you can go here. If you want to go to our organizational website and see our other programs, you can go here. If you want to go to our international arm, the Clark Institute website, you can go there and see what programs are offered. But none of these buttons along the bottom row have anything to do with facilitating microgravity experiment design and proposal writing in the classroom. None of this is important with regard to what you are doing. So I just cut out half the web content for you. Does everybody understand what I did here? Okay, so now I'm going to go across the top row. There are 2 buttons, the home button and the About SSEP button, that are immediately necessary for you. If you read the home page, which is what we're on now, this is written as an executive summary of the program. You can see it says SSEP Executive Summary. It provides all of the critically important information about the philosophy of approach in STEM education and how this program works. Once you read the home page, you need to immediately read the About SSEP page, which provides a broader and deeper understanding of this program. And once you're done with that, you will then be up to speed on what I did in Chapter 1 and Chapter 2 of this webinar. The How to Participate page is not important because you're already participating. But these next 4 buttons, Flight Opportunities, Teacher Resources, Contact and Community Network website, are what you need on an ongoing basis through the entire program. Now, if we get your email addresses and we auto-subscribe you to the blog, you will get an email notification when there's a new blog post, but your server might put it in spam, or you might not get it. Who knows where it goes when it goes out into the World Wide Web. If you ever need to go to the blog archive, you go to this button. And if you're sending a delegation to the conference in Washington, D.C., you might want to learn about what a conference looks like and the experience, and what the expectation is for student delegates to present both oral and poster presentations. So here you can read all about the different conferences. Is everybody with me so far? Yeah,
Yep.
you can give us your personal emails. That's fine. Sure, not a problem. So now I'm going to go back to the Flight Opportunities, Teacher Resources, Contact, and Community Network website web buttons. Those are the bread and butter buttons for you. Whenever you have a question or your students have a question, we have a flight operations team standing by 24/7 to answer those questions. But we don't want you to call us. We want you to send it by way of the contact page, because we need the question in writing. And that allows us to route the question to the right staff member, even to the right staffer at the launch services provider or NASA toxicology. The Community Network website is another website, and we can either go there by using this button, or do you see this? There's this big banner in the upper right column called Jump to SSEP Community Network website. So let me click on there, and let's see where it takes us. So now I am at a completely different website because I can see the space shuttle against a blue Earth in the banner. The website we came from, the main website, is where all of the curricular resources live. This website is dedicated to all of the communities that have ever participated in this program. So along the bottom navigation, you see SSEP in the news, the national blog, the contact button, logos and banners, a link back to the main website and the two organizational websites. And I already talked about these buttons. But if I now go across the top and I hover over communities and local partners, you see every mission flown show up. And when you go to these pages, you can read a profile of every community. You can read where they're located, what state and what town. You can read what their grade level focus was, how many students were engaged, a list of their schools, a list of all of their local partners like the Suncoast Federal Credit Union. And it has an email address of the leadership for those communities. So you can read all about the communities that have participated. I believe it's 168 total. If you hover over experiments selected for flight, all of the missions show up. And here you and your students can read a short summary of every flight experiment ever flown. This is a great place for your students to get ideas for experiments, because we are not giving them proposals. We're giving them a short paragraph on an experiment. And if your students want to do an experiment over again that's been flown, that's perfectly fine, because they still, in a proposal, have to justify why this is a good microgravity experiment. They have to do historical research with citations, providing an understanding of what we know in that discipline in terms of microgravity research. They have to design an experiment. They have to design a protocol and an analysis protocol. And then they have to write a formal proposal against a real proposal guide. So we are not expecting your students to do something seminally new to the human race. And we're not even asking your students to come up with experiments that are seminally new to the SSEP program. So this is a great place where they can get experimental ideas, but then they have to put all of the flesh on the bones, which is significant. If you hover over mission patches, you see all the mission patch page, the missions show up. And here you can see a mission the mission patches that flew for every mission, including the past 4 for Hillsborough County. And it describes the mission patch competition in each of these communities, the grade level focus, how many students engaged. If you hover over scientific return and reporting, mission by mission, you can watch a video of every PowerPoint presentation conducted by student teams at the national conference. Again, a great source of ideas for experiment design. And the In Our Own Words page is a place where you could read about what this program means to the community, from leadership, from teachers, from students, and even parents. So does everybody see the power of the content of this website here?
Yes, and Jeff, I think I've probably gone to the site 100 times, and there's more that you've pointed out just now than I knew existed. Thank you for that.
And the other thing too is once you get a little training on the navigation, you get to understand that it's very well organized. But without that training, it looks like a bunch of things to press, but it's all here. Now let's go back to the main website by clicking on this banner in the upper right column, or we could go here, go there by this button. But let's go back to the main website here. So we're going to click on it. And now we're back to the main website. And the 4 buttons that are really important are the Flight Opportunities, Teacher Resources, Contact, and Community Network website. Those are the bread and butter buttons throughout that you're going to use throughout the mission. We already talked about Contact, and I showed you the Community Network website. Now I'm going to show you the Flight Opportunities. Now, the curriculum is divided into 2 separate flavors. There are web pages, and there are PDF documents that are downloadable from the document library. Your mission is mission 13. So under Flight Opportunities, I'm going to hover over mission 13, and I see that there are 3 sidebar pages that show up. So there are 4 pages here that are part of your curriculum, the mission 13 main page and the 3 subpages. We don't have to go there. I'm going to tell you what's there. The mission 13 main page is a profile of the mission. It's a short profile that provides an understanding of the rocket that we're going to use, where it's going to launch from, how the experiments are going to return to Earth, what astronauts will be on the station when the experiment flies. And so it's a profile of the mission. Now, if we go to the subpages, the critical timeline page is a bulleted list of all critical milestone dates and deadlines. It tells you when the program starts. It tells you when the proposals are due to your Step 1 review board. It tells you when the finalist proposals are due to the Step 2 review board. It tells you when flight safety review takes place, when your experiment has to be handed to Houston. So all of your pacing charts and timelines need to marry up exactly to this critical timeline. The mini laboratory operations page, the next subpage, is the operating manual for the mini lab, and all teachers and students must know this page backwards and forwards. It provides all of the specifications of the mini lab in terms of dimensions and volumes. It tells you what material, what fluids and solids you must not use because they're prohibited. It tells you what a couple of hundred fluids and solids are that you should likely not use because they're very problematic. So if you want to, for instance, fly concentrated sulfuric acid, we're going to have a problem with that. This page also tells you about what you can ask the astronauts to do and what you cannot ask them to do. It tells you when on orbit the astronauts will interact with the experiments over the course of a month. There are 5 specific interaction days. It tells you what temperature to expect on the way up to station, while on station, and coming back down. So everything involved in designing this experiment in terms of engineering and technical constraints is on this page. And that's why it is so important for everybody to know this page. Now, the Mission 13 Mission Patch Art and Design competition page is for your art and design teachers, so they know what they need to have as a competition in order for us to allow patches to fly. And it also tells you what a mission patch needs to be. So does everybody understand these 4 pages? Yes?
Yes, Jeff, thank you.
Okay. Now we're going to hover over Teacher Resources, and we see 5 subpages here. These 6 pages, the main Teacher Resources page and the 5 subpages, are also part of the curriculum. And if I kind of walk through this, the Flight Experiment Design Competition page provides an understanding of how the competition works. So that's really important for students and teachers. The Designing the Flight Experiment page is where you're going to see all of Chapter 3 of this Skype. It starts with what is microgravity. It walks through going to the top of the mountain. It takes you into the elevator. It takes you through the ping pong balls to understanding that the International Space Station is a freely falling laboratory. It talks about experiment design by holding variables constant and changing one. And it tells you how to think about microgravity experiment design, because gravity is a very strange independent variable where you need to trick the system in thinking that gravity doesn't exist. So all of chapter 3 is in the Designing the Flight Experiment page. The one that has the mini laboratory under flight opportunities, Danielle, oh, you found it, okay. So now that's the Designing the Flight Experiment page. The document library is where you find the PDF versions of the PDF documents part of the curriculum. There you will find a document which is called the Microgravity Science Background document, which provides an overview of nine separate science disciplines appropriate for microgravity research and why. There is a case studies document that provides examples of experiments in each of those 9 microgravity disciplines. It provides a document that shows how to shut down biological experiments with fixatives and growth inhibitors. It has the proposal guide, which says what needs to be in every section of a proposal. There's a background document for students associated with the proposal guide that situates students in understanding what a proposal is. There's a background guide, there's a background document associated with the proposal guide for teachers, which includes the proposal evaluation rubric. Now then there's the 2 teachers, oh, and there's also videos from the launch services provider on the document library that allows you to understand how to assemble, fill, seal, and ship the mini labs. Danielle says that the mini lab operations page is password protected, as well as the documents in the document library. And so Mary said it's forthcoming because we sent out an email for program operations start, which has lots of vital information in it, including all the passwords. And I think that was sent out on September 4th. So you all have that now. The 2 teachers how to move forward page we're going to actually go to in a second. And then there's the FAQ, and there's an FAQ for each mission. And the frequently asked questions section is really, really good. There's a lot of great answers there. Now I'm going to go to the teacher resources main page by clicking on the top. And the best way to describe this is the main page for everything you do in facilitating student experiment design and proposal writing. All of the teacher and student resources are collected on this page for you in one place. This is sort of like your grand central station. And so the best way to say this is if we look at section 1, you see technical assistance, and it says if you have questions, use the contact button. Then the section 2 called this website, here we have collected all of the flavors of web pages curriculum. So these are the web page flavor of the curriculum with little descriptions. There's the flight experiment design competition page, the Designing the Flight Experiment page, the SSEP Mission 13 main page, the critical timeline page, the mini laboratory operations page. All of the web flavor of the curriculum is right here for you as a one-stop shop. You don't care about these other missions because they're not yours. Then section 3 talks about the document library and a hot link to the document library. Then 2 teachers how to move forward, it talks about that and a hot link to that page, and then there's a little description of the FAQ and a hot link there. So does everybody understand what this page is?
Yes.
So now I can go to the 2 teachers how to move forward page by going to that subpage by this pull down menu, or on the teacher and student resources page, I can also see that I can go there here. So I'm going to go to the 2 teachers how to move forward page, and this will be the end of the webinar. The first section says navigating this website for experiment design. So what this first paragraph says is you need to carefully read the home page and the About SSEP page, which is what I told you before. That's the first step. Then this purple text in this next paragraph says, however, teachers need to concentrate on getting students moving on experiment design. So here is the key. All the information that specifically addresses the design of student experiments, and then it lists all of that information, and then it goes on to say, are all accessed through a careful read of the teacher and student resources page, the link labeled teacher resources in the top navigation banner. Think of that page as your grand central station for SSEP experiment design in the classroom. One of its subpages is the page you are reading now. So does everybody understand what I just read? We just came from the teacher and student resources page. This is reinforcing the notion that's your main page. And now it's saying that this is one of the subpages. Now, if I go down to section 2, it says a proposed list of tasks and activities for SSEP launch and management in the classroom, provided in a reasonable order. We didn't want to just give teachers the curriculum and say, hey, figure it out. We wanted to give you an instructionally designed recipe to, in bullet form, walk through the entire program. That's what this is. This is a walk for teachers in a recipe through the entire program. And every time there is a web page flavor of the curriculum, there's a hot link. And every time there is a document in the document library you need, there's a hot link. And so this gives you a walk through the entire program in a very well organized way. Does everybody understand that?
Yes.
Okay. Now, if I scroll down, I get to section 3, which says important advice to teachers. And everybody needs to read this carefully, all teachers. What it is saying is that we urge you to make sure that every one of your student teams has a researcher to serve as an advisor. And that takes place once your students understand what kind of experiment they want to do. So if one of the student teams says, we want to look at planaria worm regeneration in microgravity, which is a great topic, they need to get a planaria worm regeneration expert. We cannot expect teachers across Hillsborough County to facilitate the design of experiments across a wide range of disciplines with no personal expertise in any of those disciplines. So the burden should not be on the shoulders alone of the teachers to facilitate this. Every team should have a researcher advisor. It would be nice if they were local, because then they can meet with them in person, and the researcher might have laboratory capabilities that go beyond what Hillsborough County has. But there may not be any planaria worm regeneration experts in your area, and that's okay, because the researcher can be anywhere. And so what this section says is you need to use Google Scholar Search, using Google Scholar Search. And there's a link to Google Scholar Search right here. And what it says is your team, in this particular example, should go to Google Scholar Search and enter planaria worm regeneration in the keyword spot. And the search will return all scholarly publications in peer-reviewed journals on the latest information, the latest research in planaria worm regeneration. We are not asking your students to read those papers. We're asking your students to go to the first page of each paper, go to the top, and read who the authors are. And listed with the authors will be their host institutions. And so on a paper on planaria worm regeneration, if it says Dr. Joe Smith is a planaria worm co-author, planaria worm expert co-author, and he's at Yale, your students should go to the Yale website, go to the staff directory, get Dr. Joe Smith's email address, and compose a really nice email saying, we are proposing from Hillsborough County to fly an experiment in planaria worm regeneration on the International Space Station. And we see that you are a world-renowned planaria worm regeneration expert and would like to know if you could serve as one of our researcher advisors. And most Dr. Joe Smiths say yes. And in the age of Skype and in the age of online video conferencing, there's absolutely no reason why any team should not have a researcher advisor somewhere on the planet. So does everybody understand that?
Yes, thank you, Jeff.
So that's it. I mean, we've now gone through the navigation, and you can see why we think that having this professional development is so vitally important to launch a program effectively and efficiently. This is not a small, this is not a small initiative. This is the real space program, and these are experiments that need to be designed against real world engineering and technology constraints and capable of passing real flight safety review at the toxicology office at Johnson Space Center. So this is an inspirational program. This is engaging the next generation of scientists and engineers in a real, authentic research experience on the high frontier. And we are honored and so happy and excited that Hillsborough County has come back for their 5th flight opportunity. And in fact, Hillsborough County Public Schools has their own space program. So you might want to think about a real name to designate this, like Hillsborough in Space, or some official name to call your very own space program. So does anybody have any questions? Oh, Mary is correcting me. It's hard to keep track. You are on your 6th mission. So anybody have any questions before we go? Yes, exclamation point 3 times. That's kind of amazing when you think about it.
So Jeff, just curious, are there other institutions or communities or districts that have the track record that we have that have participated multiple times?
Yes, so let me go here to the Mission 13 community profiles page that just was put up on the website today. So if you go to communities and local partners, Mission 13, it lists all of the 38 communities that are participating in Mission 13, and there are quick links to each of the communities, and there you are, Hillsborough County, Florida, and all of all of the communities are listed here as profiles. But at the very top, I wrote that this morning. It says, Mission 13 includes 5 communities in California and Texas, 2 in Florida, Michigan, and Pennsylvania, 3 in Maryland, New Jersey, and New York. 3 communities are focusing on university undergraduates, and it lists them there. And it says here, 3 communities are, Mission 13 is the 9th SSEP mission for Fitchburg, Massachusetts. It is the 6th mission for Hillsborough County, Florida, and Knox County, Tennessee. The 5th mission for Kansas City, Missouri, Burleson, Texas, and Pharr, Texas. The 4th mission for the University System of Maryland and Springfield, New Jersey. And the 3rd mission for Traverse City, Michigan, Galloway, New Jersey, and West New York STEM and Buffalo, Niagara, New York. Mission 13 is also the 2nd flight for 14 other communities. So you're way at the top relative to participation.
Thank you for that.
And I think if I go to your site, and we're going to put out an announcement asking everybody if we have all the partners listed. But here you go. Here's a list of all the missions you participated in, 13, 12, 11, 9, 7, and 5. So that's 6. And for each mission, you can go to your community profile, to your flight experiments, to your flight mission patches. So the links are all there. And here you have the partner institutions, Hillsborough County Public Schools, Tampa Bay STEM Network, Suncoast Federal Credit Union, United States of America and affiliated rinks, Bob Canigliaro and Casper's company, NASA Florida Space Grant, and this hot links to all their websites. And Mary, there you are down here as the Community Program Director. So everybody good with this? What is Danielle saying? This would be such an amazing opportunity for my students. I am excited to share this information with the other science teachers at my school so we can figure out how to into what we are doing, and such an awesome chance to get my co-teach students really into science. Go, Danielle, go. All right, everybody. I think it's Miller time.
I think that is correct. We have a beautiful sunset beginning to happen here in Tampa, and the weather is actually quite nice with the moisture being sucked out of the state.
Very cool.
All right, thanks again, Jeff. You're an incredible asset to science and STEM education around the world, and we are thrilled to have the opportunity to work with you and learn from you. This was a wonderful webinar, and I know that our teachers will find much value in it.
Back at you, Larry, because you're doing wonderful things for tens of thousands of students in Hillsborough County.
Thank you. Have a wonderful weekend, and we'll be in touch.
All right, take care.
Thank you, everyone. Thank you, Jeff.
Thank
you, Mary, for organizing and being such a rock star.
Yeah, Mary is the community program director for I think the vast majority of these missions, and it's like you just have this down to a science, right?
She is amazing.
Well, it's our students because we want to inspire them because that's why we do what we do. So thank you, Jeff, for your support and all of your dedication so that our students get this opportunity. And to Larry as well for all of your support.
Well, you're very, very welcome, Mary. And maybe this is, let's look on to mission 14.
You betcha.
All right, take care, everybody. Have a good weekend.
Thank you, everybody.